Michelle, Han, present for you guys today?
Michelle, wait, can you hear me?
Yeah, I can hear you. Yeah.
Okay, Michelle's not here, Rohan's not here. Yeah, that's it.
Awesome. Just want to make sure. Cool. I'll get started in a second. I'll give you guys a countdown. Let's get started in 3, 2, 1, go.
So hello, everybody. Welcome to our presentation today about repairing smart contracts with a two-layered approach. And yeah, we'll get right into it. Next.
So the big picture about blockchain technology. So blockchain technology is used in a variety of industries such as asset management, real estate, and healthcare. And as a result of having such a crucial impact in these industries, there are billions of dollars at risk. And what hackers do is they target the smart contracts that make up the blockchain. And what this paper aims to prove is that these attacks are preventable. Next slide. So a little bit of background on smart contracts. So smart contracts are self-executing contracts that are used for secure transactions without the need for a middleman. So they allow for the transfer of large sums of money between users with ease. These smart contracts are cyber attacks on these smart contracts can lead to severe consequences, but that's why this paper aims to integrate large language models, LLMs, and Slither feature extraction to classify and repair vulnerable smart contracts. Next slide.
So problems with existing models. Current solutions right now include expert-developed frameworks and deep learning models. However, these models fall short in providing specific feedback on these vulnerabilities. Additionally, the accuracy of these models vary, and more research is needed to identify the most effective methods. Static analyzers alone can miss vulnerabilities not in their known pattern database, and solely relying on LLMs may lead to false classifications due to intricate contract logic or bias in training data. Our proposed strategy combines these two methods, allowing us to provide double validation, spot discrepancies, and catch new vulnerabilities through LLMs that the static analyzer might have overlooked. Next.
So speaking of static analyzers, the static analyzer utilized for our smart contracts was Slither. So Slither, as we said, is a static code analyzer. It does not execute the code. It does not run the program, but it looks at the source code of the program and outputs list how confident it is, those vulnerabilities and those impacts. And we were able to, it's an open source program, and we were able to utilize Slither in our random forest classifier, our GPT 3.5 Turbo, and our Llama 2 models. Next.
So some of the goals we had were we wanted to integrate a multifaceted approach. So rather than using a single feature like other papers, we wanted to use both Slither outputs and source code. We wanted to have a dynamic response, so we would be able to return and repair specific errors rather than just returning whether or not a smart contract is vulnerable. We wanted to have an efficient use of memory, so we wanted to incorporate strategies to decrease computing complexity. And lastly, we wanted to have a higher precision that would improve upon the existing models.
So our proposed pipeline. So as we reviewed, smart contracts are key to the blockchain, and they encapsulate self-executing coded agreements. They're extremely immutable and transparent. However, they are extremely vulnerable to malicious intent. So our objective is to classify and repair malicious smart contracts with our proposed pipeline Dwarf, which we will explain later. So Dwarf is meant to coordinate the strengths of a static analyzer and an LLM for a robust and adaptable solution. Next slide.
So our academized repair pipeline is Dwarf, where it's data, web scrape, assemble, repair, and fine tune. Where firstly we find data sets that include Ethereum smart contract data. We generate and web scrape source code using contract address from Etherscan and using GPT 3.5. We run Slither on the source code, and this outputs vulnerability, confidence, and impact as some additional features, which are all beneficial when we're training classifiers and for training LLMs. The classifiers are mainly to determine whether or not a smart contract is malicious or not, and the LLM is to repair any malicious contracts that are found. And from there, we focus on fine tuning. So our classifiers aim to have a lower % false positive rate, and our LLMs aim to have higher successful pair rate in comparison to what current models exist. And so one of the issues we had was acquiring source code. Some initial hurdles we had were that some data sets would include source code, but there would be no label for whether or not the source code was malicious. And sometimes we had source code sometimes we had data sets that had labels, but there was no source code. So we would try to decompile the bytecode into source code, but that didn't work either. So our solution was to web scrape and generate source code. What basically happened is we would take the contract address, web scrape from Etherscan, and produce source code in that manner. We would do this for approximately 2,000 addresses, which took roughly 73 minutes. And for any contracts that were malicious, that weren't able to be extracted from Etherscan, we generated them through GPT, as you can see on the right. There were some problems with GPT not being able to generate malicious contracts due to ethical limitations. So we were able to work around this with prompt engineering. So the classifier we used was random forest classifier, which is one of the ML algorithms that we learned at the bootcamp. What it basically did was it took the source code and Slither outputs that we made earlier, and we made a bunch of different predictions. And the majority of those predictions would turn out to be the final prediction. And if the classifier found a specific contract to be malicious, it would go to be repaired by the LLM.
So for the LLMs, kind of the second part of that repair framework, we're looking to repair the smart contracts that are random forest classifier and Slither have labeled as malicious. Our first one was Llama 2 7B. So basically, this is a very new model that came out in July of 2023, so just a couple of weeks ago. And specifically, it works with 7 billion parameters. The version we use works with 7 billion parameters, whereas other LLMs, for example, GPT, uses trillions and trillions of parameters. So that means it uses little memory, and we made it more efficient using parameter efficient fine tuning, specifically a technique called QLoRa, which basically turns the 16-bit model that Llama 2 usually is and changes it to 4 bits, so it's easier to run on your computer, and it takes up less memory. And as you can see, there's other Llama 2 models as well. We were able to utilize the 7 billion parameter one and fine tune it with malicious and repaired contracts. Next. So specifically, one thing we worked with the Llama 2 models was a sharded version versus a unified version. So the version was uploaded with 16 parts, whereas unified was only 2 parts. Our question was, can the forked version be just as good? Because the forked version being the sharded version, just because that would be less memory. Next. So as you can see right here, on the left, the graph is showing the sharded version, which it's showing the train loss for the sharded version, which was not as accurate as our unified version, showing that our unified version was likely more powerful and more accurate. Next. And our hypothesis as why this was because there's a lot of complex relationships in the Solidity source code that the LLM had to parse through. So we needed that full unified version to be able to continue. Next. So the second one, it's a pretty common one. If you've heard of AI, you've probably heard of GPT 3.5. So when we worked with this to also repair smart contracts, we ran into a couple problems with it being averse to malicious code. However, we were able to get around it with prompt engineering. And one of the best parts about GPT 3.5 Turbo is that it's readily available and anyone can use it. Next. So this is the prompt that we used. As we talked about earlier, we used chain of thought reasoning, basically having the model explain what it's doing. So you can see the prompt below. The parameters we put in were the Slither outputs of the specific vulnerabilities that came from when we ran Slither on the source code, and then also the actual source code so that it could be repaired. So as you can see at the bottom, you say the smart contract you will repair is the source code, and the vulnerabilities are the vulnerabilities that we give it, and the output was repaired source code. Next.
So for our first layer, the classifier, our classifier had a prediction accuracy of roughly 89.6%, with an F1 score of roughly 0.762. our confusion matrix, we had 133 true positives, 23 false positives, 60 false negatives, and 584 true negatives.
And for our LLM results, which worked with those vulnerable contracts, what we did was we ran each contract through either the GPT 3.5 or the Llama 2 to be a maximum of 5 times to reduce the errors. So we found really good accuracy with this method. With GPT 3.5, we reduced 40 errors down to 1, a 97.5 reduction. And with the Llama 2, we reduced 60 errors down to 2, a 96.7 reduction. Specifically, there were no more high impact vulnerabilities, and there were no more medium impact vulnerabilities, meaning that we were able to repair the contracts accurately so that they could be used later on. Next. So right here is an example of repairing smart contracts. So on the left, labeled malicious contract, that's the malicious contract with the given vulnerabilities. And as you can see on the right, the updated utilized specifically, for example, the version of Solidity, which is the programming language that this is run on, is updated, and there's new methods and new lines added to the code, so that way this contract can accurately run and accurately do what it needs to do without being vulnerable to malicious attacks. Next.
So to conclude, some key takeaways. Using 2 tiers, a classify and repair tier framework, is really simple and it's really reliable. And utilizing multiple features like source code and Slither outputs is far more effective than just using one. Some next steps that we have involve maybe experimenting with transformers and neural networks for spotting malicious contracts instead of using just random forest classifier, enhancing Llama 2.7b's fine-tuning by including more layers, a larger data set, and also exploring PEFT, QLoRa for more precise contract repairs. Here are some acknowledgements that we had for our presentation and our project, our references, and we'd like to open the floor to questions. So ask if you have any questions, raise your hand. Arjun will unmute you guys.